Hi, we are Vivek and Monica, and today we will be talking about degree of freedom analysis. By this point, you have probably learned basic degree of freedom analysis and have been used to ask it in a few use it in a few problems. But how much do you really understand what's going on? Counting mass balances is easy, but what about more advanced parameters like pressure or stoichiometric coefficients? When is it possible to include them in your degree of freedom analysis, and why? And on that note, what is a degree of freedom analysis anyway? So what does a degree of freedom analysis actually do in a problem? Let's see. Say you have a problem. Here we have a basic single unit, continuous, isolated, non-reacting, closed system with overall simple mass balance equations. So let's get that basic problem up. Say we have here a dryer. We have wet sludge coming in. We have dried sludge coming out, we have hot air coming out, and we have cooler air coming in. Now I'm going to save you the semantics and the equations and all that stuff for this one unit. I'm not going to exactly go over all of the parameters, all of the temperatures, the pressures, and everything, just because we're going to be using it very simply. What we're going to be saying is we have air, water, we have sludge, water, we have sludge and water, and we have, again, air and water. So using these very simple variables, we can just sort of explain how mass balances go into degree of freedom simply. So, remember back to the first assignments of the course. There was surely a question that asked something along the lines of, how many independent equations are there when you solve a problem with X amount of species? So the answer was X amount of independent equations, because, for that unit of course, because you didn't include the total mass balance equation you do for the unit. So why not? Let's look at the overall mass balance equation here. So for our overall accounting equation for a problem like this, we have accumulation equals your in minus your out. Because this is a continuous system, we know that our accumulation equals 0. So for in, we put our total mass flow of the inlet streams, and for out, we put our total mass flow of the outlet streams. For this, we'll call it mass flow of 1 minus mass flow of 2. You can call it mass flow of feed, mass flow of out, mass flow of product, whatever you want to call it. But for our sake, let's just call it 1 and 2. Now for our individual species mass balances, we do the same, but with the mass fractions as coefficients to the flow rates. Now we know all of the mass fractions of each stream add up to 1. So if you haven't figured out yet why the total mass balance is not an independent equation, it is because basically all of the individual species mass balance equations are added together to equal 1. So if you want to look at this overall accounting equation as 0 with a coefficient of 1 and 1 minus, again, 1 and 2, the reason is because all of your mass fractions, so say your mass fraction of water coming in plus your mass fraction of dried sludge coming in, well, let's just call that sludge coming into stream 1 plus your mass fraction of air coming in plus your mass fraction of water coming in to your stream 2. Now this is a different stream 1 and stream 2 than I was just talking about, because we're now referring to the problem we were just looking at, rather than just a basic idea. So again, we have W water plus W sludge, mass 3 plus W air plus W water of our mass 4. So that should be a minus. Just to make that a little bit clearer, let me go over. I'll call this, what did I do? Call this stream 1, stream 2, stream 3, and stream 4. So, realistically, that is what our overall mass balance equation looks like for the problem we just did. But since we know that each of the mass balances, mass fractions of each stream add up to 1, we just go ahead and get rid of each of these and simply call it M1 plus M2 minus M3 minus M4 will equal our 0, or accumulation of 0. Because again, this is a continuous system. So, if we write our overall accounting equation like this here, it gets pretty difficult to look at. Now, if we want to make it a little bit harder but a little bit more accurate, we can actually distribute everything that's in the parentheses through multiplication in order to show us what the actual variables are. So, the variables in this equation aren't quite, if you're going to count them, wouldn't be W, WS, M1, WA, WW, M2. Really it would be WW times M1, comma, WS times M1, WA times M2, right? Our variables are our multiplied together factors. But for the sake of this exercise, let's forget that we can actually distribute them. Let's just look at our problem as it is. So we know again that these parenthetical additions equal 1, so we leave them out of the total mass balance. But for the sake of the exercise, let's forget they equal 1. Let's imagine that we have no clue about that. Let's imagine that we're just given this equation and that's the only information we have. Now, if you remember back to basic algebra, we learned that you can't solve for every variable in a set unless you have at least as many equations as you have variables. If you have less equations than you have variables, you end up needing to parameterize one or more of the variables in terms of the others. This, in the context of overall mass balance, is the meaning of degrees of freedom. These variables we are looking at here, right, are WW M1, our WS M1, and so on. These variables, each of them unique as I've written them in this equation, is what we need to solve for. Each variable is one variable we'll need to solve for and one equation that we'll need to have. Note, this is what we're counting when we list our unknowns under our analysis table. Our equations that we use to solve for them will be what we remove from degrees of freedom. These will be the numbers we subtract from the number of unknowns in the analysis table. So, we know our additive degrees of freedom, right? If we're going to do a degree of freedom analysis for the problem I just did, our additive degrees of freedom analysis and a non-reacting mass balance are simply the unknowns. To count the unknowns, right, let's go back to our diagram, we simply count the number of species in each of the streams. Right, so here we know that's 8. But what are we really doing in context of the overall accounting equation is we're counting each of these variables. So WW times M1, that's 1. WS times M1, that's 2. And so on will give us 8. That's actually what we're counting. So, for our unknowns, we here have 8. So what parameters are subtractive in our table? So let's see, we have mass balance equations, right, or our number of species overall. We will, of course, have our mass fractions. We will have our flow rates. We will have our ratios. Now, each of these represents something that you can count or something that you can put in terms of another variable, right? Mass balance equations are obvious examples of this, since we've already discussed how each mass balance equation is independent, right? That's necessity 1, and 2 relates the inlet mass fractions and the flow rates to the outlet. So a basic mass fraction will be 0 equals W1 of your inlet, so we'll call that 1, right, minus W1 of your outlet, so we'll call that 2, right? That's basic. Again, not referring to the problem we did, just a basic idea of what that looks like. Our flow rates will represent just relating a flow rate, such as 1, to any number. So let's call it 15 kilograms per minute. Now that is an independent equation, although it does not relate two variables to each other. It relates one variable to a number, which can then be referenced in another equation, and so on. As for our mass fractions, it does the same exact thing, right? 0.20, relating a variable we have in our equation, or a part of a variable at the very least, to a number. Now, ratios are equations relating one flow rate of one species to another flow rate of another species. So W1 times flow rate of 1 equals, say, 1/2 of our mass fraction of 2 in flow rate 2. Just as a for instance. Now all of these are independent equations, so they can be used to solve for the variables in the total mass balance because they contain these variables and these constants. So for fun, let's make things a little bit harder and take a look at a problem with steam, such as a dryer, right? Such as that one we just looked at. How do we do our variables and equations here? So let's take our overall guy right there. So how do we do these equations? Well, for sanity, let's say the problem gives you mole fractions and molar flows, just because otherwise we have to spend a lot more time doing things that we don't really want to go over in this video. We will have unknowns for each of the combined fraction and flow terms, so as many as there are species, just like we had with the mass fractions and the mass flows. This includes air, water, and your solids, right, your sludge. Next, we will have the same subtractive degrees of freedom as a non-reacting mass balance. So, go back to our non-reacting mass balance here. We're going to have the same subtractive degrees of freedom. Now, are there any more because it is a vapor problem? So let's see if we can add some there. Let's look into it. Now, dew point, right? Dew point can help us if we have the overall pressure of the system, because it gives us a mole fraction of air, right? Dew point will relate the mole fraction to our temperature at the dew point to our overall pressure, or to our pressure at the dew point to our overall pressure. So it can help us if we have the overall pressure of the steam. So if we have a dew point and a pressure, that will give us another subtractive degree of freedom here. Now, assuming saturation, we have a total pressure, we'll do the same thing. The only thing you're saying is that the dew point is at that temperature there, right? So these two things will count in the degree of freedom analysis. However, if we only have temperature and pressure of each air stream, while useful using the steam tables, those cannot directly help us solve for any of the balances variables, just because there can't be a defined volume transfer in a continuous system with steam and other gases. So in all this, we've really ignored what a basis is. Right, so say we had, I don't know, we have our 3 species, one ratio, we have two fractions, and we have one dew point with a pressure to that stream. This will end up giving us 7 subtractive degrees of freedom, and we need one more. So just like in algebra, we can parameterize these other variables in terms of each other, right? So in math, think about linear algebra. We learned that if we had only 7 equations to solve for 8 variables, we can parameterize 7 of those variables based off of one of the other variables. Now, this is essentially what we're doing when we're setting a basis. We are parameterizing all the other equations, all the other variables, in terms of the variable we set the basis for, then finding an answer based on what we set our basis as. Now, usually it's a flow rate, so if we set a basis as 100 kilograms of feed, for instance, each of our answers for flow after that should really follow per 100 kilograms of feed, which is why typically we're asked to find a ratio of 2 streams, because in that case it would cancel out. So if it were not a ratio and it was asking you, for instance, how much product comes out, and you had to parameterize, make your basis 100 kilograms of feed, then that sentence in itself should say the product is blank per 100 kilograms of feed. Now let's look at the opposite scenario when you have an overdefined problem. Let's say you have the opposite scenario. You have a flow rate and you didn't set a basis, and rather than one ratio you have 2 ratios, so you end up with -1 degrees of freedom, right? So you have more equations in this scenario than you have variables, which means we can solve for our variables and then double check or triple check or check again for however many equations we have. So in this instance we have 9 equations for our 8 variables, so we could double check it, right? Now this happens in our degree of freedom when we have too few unknowns in our equations and we have a negative degree of freedom. So what we can do is use our equation to find our answers. But if we find that it's not consistent, what we have to do is pick an equation to nullify and then give an explanation as to why that's the one we chose that is consistent with the structure of the system. Again, typically that'll be a flow rate. Now that's all you really need to know to use degree of freedom proficiently. So let's try to put that into use with a problem. Alright, so now Monica is going to go through using degree of freedom analysis and solving a problem, specifically the problem that I wrote up to begin with.
Okay, so you have your dryer and wet sludge coming in. And the problem says it's 30% weight of water, so then you have water and sludge, and this is 30%. Ooh, that's bad. And so, you know, the sludge is 70%, and you have dried sludge coming out. But we're going to say it still has some water in it, but it's reduced to 20% water by weight. And sludge is going to be 80%. And then you have hot air coming out, and that's at 110 degrees Fahrenheit with a dew point of 89.6 degrees Fahrenheit at a pressure of 700 millimeters of mercury. And going in, you have air at 75.2 degrees Fahrenheit with a relative humidity of 40%. And a pressure of 800 millimeters of mercury. And the problem says that a wet sludge containing 30% by weight of water enters a dryer at a rate of 300 pounds per hour. So this is 300 pounds per hour. And it's dried by air with a relative humidity of 40%. And we have to use the rest of the information in this diagram to solve for the amount of moist air required for the process. So we are trying to find this air right here.
Alright, so now that we have a problem to look at, our dryer problem that we used originally, let's do the degree of freedom analysis for this dryer problem. So if we remember our degrees of freedom analysis, we'll start simply, right, by counting our unknowns. For these unknowns, we have to simply count the number of species in each stream, which is essentially counting the number of variables in the overall counting equation. So in each stream, here we have air, we have water and sludge, we have air and water, and we have water and sludge again, so that is 8, like we did before. Now the next thing we can look at is our mass balance equations. We have 3 separate species, right? We have air, we have water, and we have sludge. Somebody just got injured in the room over. So we have 3 mass balance equations. Now our next is our mass fractions, right? And because we typically only count the mass fraction, only one mass fraction, right, when we know the total number of mass fractions of 2 species in a stream, right? So we know water and sludge add up to 1. So because we already knew that, sludge doesn't count as its own mass fraction, right? We know this because we've done degree of freedom before. So for our total number of mass fractions, it's only going to be 2. I believe, yes, these are mass fractions. So they will be little omegas. Now on top of our mass fractions, we have to look at our flow rates. So what flow rates were given? 300 pounds per hour of air. So we have flow rates. We have one of those guys. At the same time, we have our relative humidity, and we have a dew point here. Now for each of these, our relative humidity and our dew point, we are given the pressure at that point. So let's think about how we use relative humidity. So your relative humidity for anything is equal to your partial pressure of H2O over your vapor pressure of H2O at whatever temperature you're looking at. So given the relative humidity, we're able to find if we have the current pressure and the current temperature, one or the other, if we have that current pressure or temperature, we are able to find this P star. So we know that, and that'll give us our partial pressure of H2O. So our partial pressure of H2O is equal to our total pressure times our mole fraction of H2O. So what does this partial pressure of H2O give us? Well, nothing unless we also have this total pressure, which we do, right? We do have our total pressure there. That's our 800 millimeters mercury. So we have this, so we're able to find our mole fraction of H2O. So we could count that into a mass fraction, right? Because mole fraction and mass fraction, when you have a flow rate of something, can go very easily back and forth. But let's just go ahead and call that a relative humidity. So again, this is why we need things like pressure, we need things like temperature in order to actually call relative humidity a subtractive degree of freedom. So that's our relative humidity. Now let's go back. And what other specifications were we given? We were given the dew point of the outlet steam. So with this dew point of outlet steam, we have a dew point, we have our degrees Fahrenheit, and we have 700 millimeters mercury, our pressure. So with a dew point, we know that our P star of at this certain temperature, we know that it'll be saturated at that temperature, right? All right, so your dew point is your temperature, in this case given as 89.6 degrees Fahrenheit, at which your steam will start to condense, or at which your liquid will start to evaporate, right? It's on your vapor-liquid equilibrium line, the dew point. So when you're given a dew point of something like 89.6 degrees Fahrenheit, with a temperature and a pressure, more with the pressure than the temperature, you're able to use dew point to find via your steam tables your partial pressure of H2O, and thereby your mole fraction of H2O. So we can go ahead and count in dew point there. So, if I'm not mistaken, I believe that is all we should need, right? Counting all these fellas, we got 5, 6, 7, 8. So our degree of freedom is 0, so it is properly specified. Perfect. All right. So that's an example of how you can use degree of freedom proficiently using STEAM in a STEAM problem. So learn how to spot what specifications in a problem statement are giving you equations to use for your variables, and you'll be able to find degree of freedoms for pretty much any problem. This has been Vivek and Monica, and thank you for watching.